Welcome to Study Loop.
For this question, we're looking at the disintegration, right, of a deuteron due to a photon coming in that actually splits it up into a proton and a neutron. We are given that we can assume that both of them have the same speed, right? They're moving off in opposite directions, the same speed, and the velocity measured of the proton is given in the table as shown. And we want to plot, right, a graph of actually v squared versus 1 over lambda. All right, so now to get rid of that, we can write down, right, v squared and 1 over lambda on a separate table, right, as shown. And then we're going to plot these values, right? So we're going to plot v squared versus 1 over lambda, which means that v squared is the y-axis, right? This is y. This will be the x-axis. All right, so very simple. If you plot it and draw a straight line, what you should get is something like this graph, right? A straight line. Now, to figure out why is it a straight line, now we know that v squared is associated with kinetic energy, right? Because we have half mv squared, right? V squared is inside. What about 1 over lambda? Well, if you know the energy of a photon, it's given as hc over lambda, right? You see this 1 over lambda appearing over here. And now how do we equate this kinetic energy with this energy of a photon? When we know the photon enters, and then it afterwards splits, right? The energy is splits between the photon, the proton and the neutron, right? And so therefore, we can equate this to actually the binding energy, because the energy of photon is absorbed, some of it goes to the binding energy, and then the rest is actually given to the proton and neutron as kinetic energy, right? So again, energy of the photon is split up into the binding energy, which is a constant, right? Binding energy for the deuterium, plus the kinetic energy of the kinetic energy of the proton and the neutron. Now we're given that because they are the same speed, so basically it's the same value multiplied by 2. Right? So what we get is just mv squared, right, where m is the mass of the neutron or the proton, which is about the same. Right, we're going to assume that they are the same for now. Okay, actually we shouldn't, because it's slightly different. And so we have mp plus mn, mass of neutron, times half v squared. Right, and we see that if we were to move this around, right, we move the binding energy to the left hand side, this will be half is equals to the energy of the photon, which is hc over lambda minus binding energy. You can see that this is a straight line equation where v squared is the y, 1 over lambda is the x. Right, so therefore we are expected to get a straight line. Now the next part of this question, we want to find out what is the slope. right, using our graph. Your graph might be slightly different, but the method to find the slope is the same. You take rise over run, right? So in this case, we're gonna try to find the slope. We can take the extreme values, right, which is this point over here and this point over here, right? These values. So we get now remember the y-axis is the v square, so that's the rise over the run. Right, put that to the calculator. And of course, we can't forget the units as well, right? So in this case, for v square, the y-axis is 10 to the power 13. Let me just put that in. And for the x-axis is 10 to the power 12. Alright, so this is the gradient that we should get. And if you want, in terms of units, is meter cube second square. Now using this value, we want to try to find, we also want to find the y-intercept. Alright, so to get the y-intercept, now to get the y-intercept, what you should need to do is to extend your graph, right, all the way past the y-axis, such that it cuts x equals to 0, and you want to see where the y value is, right? So for my graph, this is a bit difficult because it's not at 1.9, but using your own graph, you should be able to get a y-intercept. That is roughly negative 2.156 times 10 to the power 14. And the unit is meter square per second square because you are v square, right? Now using this value, and of course the value of the gradient, can actually find a few the values for the proton mass as well as the binding energy of the deuterium. So we're going to do that. Right, so we have y-intercept. That is when our x is 0, which is our x is 1 over lambda. So when 1 over lambda is 0, this term goes to 0. So binding and our y-intercept is basically the value of the v square over here. So all we need to do is to substitute in v square as this term, as this value, and we will get negative of the binding energy. Right? So we get mass of the proton plus mass of the neutron multiplied by v squared. Sorry, the negative is cancel out, right, from the binding energy. And we will need to convert this U into kilograms by multiplying by 1.66 times 10 to the power 27. Sorry, minus 27. Alright, and our binding energy should be about 2.22 MeV. Now to get the mass of the proton, we're going to use the gradient. Alright, so remember from our equation, the gradient, right, is if you were to just move it over, we get right, so HC balloon. Right, so this is our gradient. We know the standard values of H and C. Now we can use that to find the mass of the proton. Right, we're going to assume mass of the proton is very close to the mass of neutron, so that just this is just 2 MP, right, 2 times the mass of the proton. And then the half and the 2 cancels out. Equate this to the gradient, which in our case 120.93. Sorry, this is not part of the gradient, right? This is the gradient. So the mass of the proton, BH C divided by 120.93. You should get about 1.64 times 10 power minus 27. Right, which is pretty close.